Have you ever wondered why your new laptop boots up in seconds while your old one took minutes? The answer lies in a tiny circuit board, no bigger than a stick of gum, that's revolutionizing how we think about computer storage. Today, we're diving deep into the world of M.2 NVMe SSDs, a technology that's changing everything we know about speed and performance. But here's the question that should make you pause. Are you still using outdated technology without even knowing it? Stick around, because by the end of this story, you'll understand why this matters more than you think. And if you're finding value in this journey of discovery, consider subscribing to our channel. We break down complex technology into stories that actually make sense. Let's start with a truth that many people overlook. Storage technology has always been the quiet workhorse of computing, rarely getting the spotlight it deserves. For decades, hard drives dominated the landscape, spinning metal platters at thousands of revolutions per minute, reading data with mechanical arms that moved back and forth like tiny record players. Then came the solid-state revolution and everything changed. Suddenly, we had drives with no moving parts, relying instead on flash memory chips that could access data almost instantly. The difference was like comparing a horse-drawn carriage to a sports car. But here's where the story gets interesting. When solid-state drives first appeared in the mid-2000s, they faced a fundamental problem. The technology inside them was revolutionary, capable of incredible speeds. But they were forced to communicate with computers using interfaces designed for those old spinning hard drives. Imagine having a Formula One race car but being required to drive it on dirt roads built a century ago. That's exactly what was happening inside millions of computers around the world. The first generation of SSDs came in a familiar package, the 2.5-inch form factor, the same size as laptop hard drives. They connected to motherboards using SATA cables, just like their mechanical predecessors. For many users, this seemed perfectly fine. After all, these early SSDs were already 5 to 10 times faster than traditional hard drives. Boot times dropped from minutes to seconds. Applications launched almost instantly. It felt like magic. But beneath the surface, a bottleneck was forming, one that would eventually demand a completely new approach. To understand why, we need to talk about SATA 3.0 and something called AHCI. These standards were created in an era when storage was fundamentally different. SATA 3.0, released in 2008, offered a maximum theoretical bandwidth of 600 megabytes per second. At the time, this seemed more than adequate. After all, the fastest hard drives could barely reach 150 megabytes per second. But as flash memory technology improved year after year, SSDs began pushing against this ceiling. By 2012, high-end SATA SSDs were already maxing out the interface, unable to go any faster despite having the internal capability to do so. The problem ran even deeper than bandwidth. AHCI, which stands for Advanced Host Controller Interface, was designed with spinning hard drives in mind. It assumed that storage devices would have high latency due to mechanical delays. It was built for a single command queue with a maximum depth of 32 commands. This architecture made sense when you were dealing with a spinning platter that can only read from one physical location at a time, but flash memory works completely differently. It can handle thousands of simultaneous operations, accessing multiple memory cells in parallel. Forcing modern SSDs to work through AHCI was like making 1,000 people stand in a single file line when you could have them spread across multiple checkout counters. This is where the M.2 form factor enters our story. Engineers realized they needed to rethink everything, not just the interface protocol but the physical design itself. Why use bulky 2.5-inch enclosures and cables when you could create something smaller and more elegant? The M.2 specification emerged as a solution, defining a compact expansion card that plugs directly into the motherboard. These drives are thin rectangles of circuit board, typically 80 millimeters long and 22 millimeters wide, though other sizes exist. Installation couldn't be simpler. You slide the drive into an M.2 slot at an angle, press it down flat, and secure it with a single tiny screw. No SATA cables. No separate power connections. Everything happens through that one slot. The elegance of this design goes beyond convenience. By eliminating cables, you reduce signal interference and latency. By connecting directly to the motherboard, you create a shorter, cleaner electrical path. But the real breakthrough wasn't in the physical form factor. It was in what that M.2 slot could carry, the PCI Express bus. PCIe Express, or PCIe as it's commonly called, had been around since 2004, primarily used for graphics cards and other expansion devices. Unlike SATA, which was purpose-built for storage, PCIe was designed as a high-speed, general-purpose interconnect capable of massive bandwidth. The earliest PCIe generation offered significantly more throughput than SATA. By the time PCIe 3.0 became standard, a single PCIe lane could handle nearly 1 GB per second. Most M.2 ME drives use 4 lanes simultaneously, giving them access to roughly 4 GB per second of bandwidth. Compare that to SATA's 600 MB per second, and you begin to see why this matters. But bandwidth alone doesn't tell the whole story. You could have a massive highway, but if the traffic rules are inefficient, you'll still have congestion. This is where NVMe comes in, and it's arguably the most important piece of this entire puzzle. NVMe stands for Non-Volatile Memory Express, and it's a storage protocol built from the ground up for solid-state drives. Unlike AHCI, which was adapted from older standards, NVMe was designed by engineers who understood how flash memory works and what it needs to perform at its best. Think about it this way. When you're running a modern computer, you're not just loading one file at a time. You might be opening an application while the operating system checks for updates in the background, while your antivirus scans files, while your browser loads dozens of tabs simultaneously. Each of these actions generates storage requests. AHCI, with its single queue and 32 command limit, has to process these requests one narrow stream at a time. It's like having a single phone line trying to handle all the communication needs of a large office. NVMe changes the game completely. It supports up to 65,536 queues, and each queue can hold up to 65,536 commands. To put that in perspective, we're talking about millions of potential simultaneous operations. This isn't just a quantitative improvement, it's a qualitative transformation. NVMe allows the drive to organize and prioritize work in ways that were simply impossible before. It can group related commands together. It can execute operations out of order when doing so improves efficiency. It can spread work across multiple flash memory chips in parallel, same way a modern CPU spreads work across multiple cores. The reduction in latency is equally dramatic. When your CPU sends a storage command through AHCI, it goes through multiple layers of software overhead, each adding microseconds of delay. NVMe streamlines this entire path, cutting latency by more than half in many scenarios. For everyday users, this translates to applications that launch faster, files that save instantly, and systems that feel incredibly responsive. For professionals working with large video files or complex databases, it's the difference between productivity and frustration. Real-world examples help illustrate the impact. Consider a video editor working with 4K footage. A single minute of uncompressed 4K video can exceed 20 gigabytes. When scrubbing through a timeline, the editing software constantly loads and unloads chunks of video into memory. With a SATA SSD, this process is limited to about 550 megabytes per second in practice. You'll see occasional stutters, delays when applying effects, frustrating waits when rendering previews. Switch to a good NVMe drive, and those same operations happen at 3,000 to 5,000 megabytes per second. The timeline becomes fluid, effects apply in real time. The entire creative process transforms because the storage is no longer the constraint. Or consider game developers. Modern game engines stream assets dynamically as you move through virtual worlds. High-resolution textures, complex geometry, audio files all need to load seamlessly without creating visible pop-in or stuttering. Consoles like the PlayStation 5 and Xbox Series X both use custom NVMe solutions specifically because older storage technologies simply couldn't keep up with the demands of current generation games. This isn't just about faster load screens, though those are nice. It's about enabling entirely new approaches to game design, worlds that feel more alive and responsive because the underlying technology can finally keep pace with creative ambition. But here's something crucial that many people miss when shopping for upgrades. Not all M.2 drives are created equal, and this is where confusion often happens. The M.2 form factor is just a physical specification. It defines the shape and size of the card, nothing more. An M.2 drive can use either the SATA protocol or the NVMe protocol. From the outside, they might look identical, two small circuit boards with the same dimensions and the same edge connector. but internally they're completely different animals. An M.2 SATA drive gives you the convenience of the compact form factor and cable-free installation, but it's still limited to SATA speeds. You will see the same 600 megabyte per second ceiling as a traditional 2.5-inch SATA SD. There's nothing inherently wrong with these drives. They're perfectly adequate for basic computing tasks, and they're often cheaper than NVMe alternatives. But if you're expecting NVMe performance and you accidentally buy an M.2 SATA drive, you'll be disappointed. The only way to know for certain is to check the specifications carefully before purchasing. Motherboard compatibility adds another layer of complexity. Older motherboards may have M.2 slots that only support SATA, not PCIe. Some motherboards have multiple M.2 slots, but they don't all work the same way. One slot might support both SATA and NVMe, while another might only support SATA. Some slots share bandwidth with other ports, meaning if you populate the M.2 slot, certain SATA ports or PCIe slots become disabled. This isn't anyone trying to make things difficult. It's simply a limitation of how many PCIe lanes a CPU and chipset can provide. But it means you need to do your homework before buying. PCIe generations add yet another variable. We're currently on PCIe 4.0 becoming standard, with PCIe 5.0 starting to appear in high-end systems. Each generation roughly doubles the bandwidth of the previous one. A PCIe 3.0 NVMe drive might reach 3,500 megabytes per second. A PCIe 4.0 drive can exceed 7,000. PCIe 5.0 drives are pushing toward 14,000 megabytes per second. But here's the catch. To take advantage of these higher speeds, every link in the chain must support them. Your motherboard, your CPU, and your drive all need to speak the same PCIe generation. Installing a PCIe 4.0 drive in a PCIe 3.0 slot will work, but the drive will only run at PCIe 3.0 speeds. So what does all this mean for you? If you're building a new computer or upgrading an existing one, understanding these distinctions can save you money and frustration. For general use, web browsing, office applications, even casual gaming, a good PCIe 3.0 NVMe drive offers more than enough performance. You'll pay less than for the latest PCIe 5.0 drives, and honestly, you probably won't notice the difference in everyday tasks. But if you're doing professional creative work, running virtual machines, working with databases, or simply want the absolute best performance available, investing in a current generation NVMe drive makes sense. The broader lesson here transcends technology specs. We live in a world where upgrades and improvements are marketed constantly, where there's always something newer and supposedly better. The key is understanding not just what's available, but what actually matters for your specific needs. A carpenter doesn't need every tool in the hardware store, just the right tools for the job. The same principle applies to technology. Knowledge gives you the power to make informed choices rather than falling for marketing hype or overpaying for capabilities you will never use. There's also something profound about how innovation happens. The jump from SATA to NVMe didn't come from a single breakthrough. It came from recognizing that a system designed for one purpose had outlived its usefulness for another. It came from engineers willing to start fresh rather than endlessly patch an aging standard. Sometimes progress requires letting go of what worked before and embracing something fundamentally different. That's a lesson that applies far beyond computer hardware. As we close this exploration, ask yourself, how many other areas of life are we still using old interfaces for new capabilities? Where are the bottlenecks in your own workflows, your own thinking, your own habits? Technology evolves quickly, but human adaptation often lags behind. The tools are available, but only if we recognize when it's time to upgrade our approach. I'd love to hear your thoughts. Have you made the switch to NVMe? Did you notice the difference? Or are you still running perfectly happy on older storage technology? Drop a comment below and let's continue this conversation. Remember, understanding technology isn't about memorizing specs. It's about knowing enough to make choices that serve your needs and your goals. I hope this story gave you not just information, but perspective. If you found value here, consider subscribing. We'll continue exploring the technologies that shape our world, always looking beyond the surface to find the meaning underneath.